let me know if it doesn't change. So I'm going to talk about the basic science of muscle wasting. And a lot of my group's work is on microRNAs, so I will introduce those and talk to you about what we've been doing. As you will all be aware, losing muscle mass is a common comorbidity of a whole range of diseases. And here's a list of some of them that are involved. And in all cases, it's a fairly bad thing to happen. A lot of the data I'm going to present to you comes from two groups, that is patients with COPD and patients on or about to be admitted to the intensive care unit. But what I want to start with is a bit of a philosophical question that is often not asked, and that's why it happen. And I personally think it's an evolutionary response. And it goes back to before we had medicine, before we had the ability to look after ourselves. And if we got injured or ill, we had to find the energy to repair the damage, to fight the infection. And that was the key thing. You had to be able to do that, otherwise the disease would kill you. So what did you do? You needed the energy. You could either go out and hunt, but that might not be successful. You could try and go out and scavenge, but that might not be successful. So you had to do something else. So what you do is you use your resources, and one of the main resources you've got is your muscle, and that provides the amino acids to repair the damage, to fight the illness, and to make you better. And if that works, that's great. You can go out, you can hunt, you can regenerate your muscle, and if it doesn't, if it's unsuccessful, you die. But that was going to happen anyway, so evolutionarily it doesn't matter. But what we do now is we have medical intervention, and we sustain people. We also have, and that will generate chronic illness. The person is not necessarily cured. They still have COPD or heart failure or whatever it is, but they just aren't dead. What we also have are a whole series of lifestyle choices that we make that lead to chronic illness. And here, if the signal is not the amount of amino acid or whatever that's available, it is the state of illness, you will continue to have muscle wasting, because the muscle will still be thinking we are in a sick state, so it needs to provide the amino acids or whatever to repair that damage. So therapy doesn't repair, it maintains, but the patient doesn't die. So what we end up with is continual muscle loss and physical frailty. So basic biochemistry, we have protein that we are making all the time from amino acids through our ribosomes. We have protein that we are breaking down all the time through the protease systems. This is a continual cycle, and if you actually look at the fractional synthetic rate data that has been generated, we turn over our muscle completely within between 40 and 100 days. If you take a starved rate of protein synthesis, it's about 1% per day. If you take a fed rate, it's about 2 and a bit % per day. So take something in between and you're going to get about standard, and that fits in with measured skeletal muscle myosin half-life of about 30 days, although that data comes from rabbits. As you know, if we are active, we will reduce protease activity and increase ribosome activity. If we have good nutrition, we'll again suppress protease activity to some extent and increase our ribosome function. And if we have inflammation or a demand for repair, we will do the opposite and activate the protease system and inhibit the ribosome system. There are proteins that we know activate protein synthesis and in response to activity and nutrition. And there is a whole catalogue of proteins, and other things like cortisol, and I've only put in a few, that activate inflammation and demand for repair. But one of the things about these factors on the right-hand side is that they feed back, they inhibit activity, and they inhibit our desire for nutrition, probably because evolutionarily we had to stop walking, we had to stop hunting to reserve our resources until we were better. And one thing you don't want to be is hungry, because that's going to drive you to go out and get food. The other thing about this system and this rate of protein turnover is that actually very small changes in muscle protein synthesis or muscle protein breakdown leads to rapid muscle loss. So if you increase from 1% to 1.1% as your fractional breakdown rate with no fractional change in your fractional synthetic rate, you will get 10% muscle loss within 6 months. Sorry, 3 months. There's a thing in the way. I can't see what I'm within 3 months, and that's greater than the 5% muscle loss in 6 months that is in the Fearon diagnosis of myopenia. So the questions we are asking is, can we increase the understanding of the underlying biology of muscle? Given that muscle wasting is so very variable, can we identify those at greatest risk? And can we develop inhibitors for this process? One of the models we've been using was developed by Mark Griffiths and Mike Polke, which is this human eye model. In this, patients are having major aortic surgery with coronary pulmonary artery bypass, cardiac pulmonary arteries bypass. And the good thing about this is that the patients already have disease, and you'll see why I think that's important in a bit. But we are going to give them a huge inflammatory insult, so we know when that's going to happen, and it's also going to be similar throughout all the patients. We can assess them preoperatively. We can measure their muscle strength, their muscle bulk, and we can measure things like their lung function, their cardiac function beforehand. At the point of surgery, we've taken open muscle biopsies, and on day 1 we've taken closed muscle biopsies, and we've sampled their blood throughout, and then we can measure their muscle strength and their muscle bulk 7 days later. And we've done transcriptomics on the muscle biopsies. We've looked at microRNA expression in the muscle biopsies, and we've done metabolomics and proteomics on the blood samples. And the thing about this model is that about 50% of the patients will lose 10% of the cross-sectional area of their rectus femoris in 7 days. Compare gene expression between the day 0 biopsy and the day 1 biopsy. There is a marked inflammatory response, which is exactly what you would expect. And this is the gene enrichment for those genes increased on day 1 compared to day 0. If you look in the circulation, again, you have a large increase in the acute. You have a large acute phase response, which again is exactly what you'd expect. Within looking specifically at the ubiquitin ligases, which are involved in driving muscle wasting, both estrogen and MRF go up between day 0 and day 1. In those defined as wasting, that is those who lose more than 10% of their muscle mass, the increase in estrogen is a little bit bigger than the increase in MRF. But in the wasting patients compared to non-wasting patients, but neither MRF nor NED4 are different in the extent of change. We've done a previous study compared to this one, looked at GDF15 expression, and GDF15 increases in response to this surgical process. And those patients who waste have a larger elevation of GDF15 than those who don't. But actually, they also start with slightly more GDF15 than those who don't waste. If you look at circulating metabolites, you can take patients at day 0. They get a significant change in metabolites present in their circulation on day 1, unsurprisingly, and then that returns back to normal. This is their metabolic profiles on day 3 and 7. Wasters do have a different metabolic profile compared to non-wasters. You can see here they get a large increase in creatinine. Both groups get an increase in creatine, but you can see more protein release because you've got more N-acetyl histidine in circulation on day 3 in the wasters compared to the non-wasters. The size of the insult is remarkably similar if you look at cortisol. So cortisol goes up to the same extent in both wasting and non-wasting patients, shown here. But cortisol metabolism is slightly different, and there's a little bit of a reduction in the production of cortisone, and you get the 4-hydroxy version of cortisol that's the metabolite, 4-dehydroxy version. There is slightly greater oxidative stress in the wasting patients, but possibly most importantly, this shows just adipoyl-carnitine, but there's a whole range of carnitine derivatives of lipids that are increased to a greater extent in the wasting patients than in the non-wasting patients. And these are often higher in the wasting the patients who will go on to waste before you start. And this is a marker of mitochondrial dysfunction because the carnitines lipids are taken up into mitochondria in as acetylated carnitines. If the mitochondria aren't working properly, those carnitine derivatives get exported into the circulation. So a lot of what we do is based around microRNAs. What are microRNAs and what do they do? Well, this is a very simple diagram. DNA makes RNA makes protein and RNA gets degraded. What microRNAs do is they interrupt the production of specific proteins and they cause the degradation of specific RNAs. One microRNA will target a lot of RNAs to block its translation or promote its degradation, but it'll be a set of mRNAs that get targeted. When we originally screened for differences in microRNA expression in the quadriceps of patients with COPD, what we found was one set of microRNAs that were increased in the COPD patients compared to age-matched controls. These come from a single cluster that exists on the X chromosome. When we compared patients who had similar disease severities but different muscle masses, we found that there was one microRNA that was markedly elevated in those with a low fat-free mass, which is miR675, and another cluster of microRNAs that were more elevated, more highly expressed in the patients who maintained their muscle mass. The interesting thing about these is that this you express from the chromosome you inherited from your mother, and these you express from the chromosome you inherited from your father. Now this miR424-542 cluster, when we looked in a larger cohort, they were increased in the patients, which was nice. But what was quite surprising was that actually their expression level was inversely proportional to their lung function. This is in COPD patients. If you looked in patients from the intensive care unit, we had an absolutely enormous increase in the expression of these two microRNAs. This is an over 50-fold elevation. If you take our patients who are about to have surgery, then now instead of associating with lung function, you get an association with the state of their heart. There's a weak association, inverse association with their left ventricular ejection fraction. But if you look in the proteomics we've done, in circulation, we can find markers of heart, which shouldn't be there. And the amount of these microRNAs is directly proportional to the amount of these cardiac proteins that are present in the circulation. What's perhaps more surprising is if you look in the day 0 biopsies before they have had surgery, you can tell how much muscle they're going to lose in the next 7 days, because we have this direct association between the expression of miR542 and miR424 and the amount of muscle that will be lost. We also have an inverse association with one of the microRNAs from that C19 microRNA cluster, which I showed you earlier on. We haven't measured all of them because there's about 40 of them. We've only measured a couple, and both show this inverse association. So what do these microRNAs do? Well, miR542 and 424, they inhibit IGF-1 signaling, they promote TGF-beta signaling, but probably more importantly, they target structural components of the ribosome. So miR542 inhibits ribosomal protein expression, and miR424 inhibits ribosomal RNA synthesis. This reduces ribosomal content. It actually induces a thing called ribosomal stress, which will lead to p53 activation. Ribosomes are synthesized, ribosomal RNAs are synthesized from a different system to messenger RNAs. they use this polymerase 1, RNA pol 1. And what MIR-424 does is it targets both UBTF, which is an essential transcription factor for this process, POLR1, and this protein here, RRN3. So there are three components of the process that are targeted. And just to show you that that is true, here is the effect of our microRNA on the expression of UBTF in cells, both at an RNA level and at a protein level. If you then overexpress MIR-424 in the tibialis anterior of a mouse, which we did by sticking it on the end of a GFP, you can look at what happens in the muscle. And in this because we electroporate these into the tibialis anterior, we can use the control leg, which just expresses GFP, against one that expresses both MIR-424 and the GFP. You get a large increase in MIR-424 expression, unsurprisingly, and a rapid reduction in TA weight, and this is in 3 days. If you look at the fibers that express GFP in the left tibialis anterior are very similar to those that don't express very much GFP in the same muscle. But when you look in the other muscle, the ones that haven't taken up any or much of the plasmid are much larger than those that have taken up the plasmid and are expressing the microRNA. And this you can quantify, which we've done here. If you look at gene expression, the amount of the ribosomal RNAs goes down and the amount of UBTF goes down. And if you look in patients with intensive K-acquired weakness, you see that there is a reduction of UBTF and a proportional association of UBTF expression with the amount of the 18S rRNA, which is what you predict. Now, MIR-542 does target cytoplasmic ribosomes, but it also targets mitochondrial ribosomes. Mitochondrial ribosomes are different. They have their own mitochondrial ribosomal proteins. They make a 12S rRNA and a 16, or they are made from a 12S rRNA and a 16S rRNA, and they synthesize 13 proteins that are required for the electron transport chain and for the ATP synthase. MIR-542 knocks down MRPS10. It binds to a whole load of mitochondrial ribosomal proteins. We haven't checked whether it knocks these down as well, but I suspect that it does. And in doing that, it stops the production of this small ribosomal subunit. And one of the features of the 12S rRNA, and the same is true of the 18S rRNA, is without their proteins, they are unstable. So what you end up with is, a reduction in the 12S rRNA in the presence of the microRNA, which you can start to return if you put in an antagomer. Now, if you look at mitochondrial membrane potential, you get a marked reduction in mitochondrial membrane potential that then returns to normal in the presence of the antagomer. If you do the same trick in making mice, you can get, again, a marked reduction in the weight of the tibialis anterior and very small fibers that express both the GFP and the microRNA compared to those that express just the GFP. You get a marked reduction in complex 1 activity, mitochondrial membrane potential, and a huge reduction in the 12S rRNA expression. Now, if you look in patients with COPD or intensive K-acquired weakness, you see a reduction in both the 12S and the 16S, which is what you'd expect for a disease where you've got fewer mitochondria, and that is an often noted phenomenon. But perhaps more importantly, if you compare the 12S to the 16S rRNAs, you find that in the COPD patients and in the intensive K-acquired weakness patients, you have evidence of mitochondrial ribosomal dysfunction, which is what is being caused by the MIR-542. If you then go and just do gene set enrichment analysis this is from the intensive K-unit patients that you compare it to MIR-542, but you can do this from the COPD patients in exactly the same way. You find it is negatively associated with oxidative phosphorylation and positively associated with genes associated with the p53 pathway, which is exactly what you'd predict if you were getting mitochondrial ribosomal dysfunction. So, can we change any of this? Well, puromycin is a method of measuring protein synthesis in cells, because puromycin gets added on to the growing chains, and you can quantify the amount of puromycin in a preparation. So we've developed both. Initially, we developed locked nucleic acid antagomeres, but we've now also developed 2-O-methyl RNA antagomeres for miR-424. And you can see you get a reduction. If you add in miR-424, you get a reduction in protein synthesis that you can reverse with the antagomere. In the presence of the antagomere alone, you get an increase in protein synthesis. We've then gone and put these into mice, and the 2-O-methyl, I'll show you data from the 2-O-methyl RNAs. We've taken old mice, we have put in the antagomere into the left leg and a control into the right leg and a control into the left leg. And then we have given the mice a respiratory syncytial viral infection. We leave them for 8 days and you get muscle loss in those 8 days. So here is what happens in just old mice. You can see that when you put in the antagomere, you get an increase in fiber diameter. In old female mice, given the viral infection, you get a larger increase in fiber diameter, and you see a similar increase in fiber diameter in old male mice. And if you look at gene expression, you can see that we are getting exactly what we'd expect: an increase in POLR1, an increase in UBTF, and no change in other things that we might not expect to change in response to this particular microRNA. So that's fine, but that says that disease severity drives a response, but we know that not all patients respond the same. So we took our transcriptomics and I did a technique called weighted gene co-expression network analysis. And this allows us to form all the genes into modules, to look at similar groups of genes, and then to correlate them against phenotype or against something else. And we correlated them against all the microRNAs. And what dropped out of this was quite surprising, because this is our day one transcriptomics. The thing that gives us the greatest association with any module is our previous day's miR-675. This was the microRNA I showed you that was markedly elevated in patients who lost muscle mass. So what's happening? If you now plot the correlation coefficient of each gene with miR-675 and the fold change in their expression, what you find is that genes that go up are positively associated with the previous day's miR-675. Genes that go down are negatively associated with the previous day's miR-675. If you look at the gene enrichment for this, these are associated with as MYC targets or as inflammatory genes. These are all muscle biology genes, or not all muscle. These are enriched for muscle biology genes. If you do this similar analysis looking in our COPD patients for positively associated gene groups, you find enrichment with miR-675 for MYC targets and for inflammatory signaling components. miR-675 comes out of a gene called H19, and if you now look in healthy people and you look for enrichment in old individuals, you find that H19 is associated with inflammatory signaling again.
Just as a time warning, we're down to the last 5 minutes.
Okay, sure, that's fine. So we'd previously found that miR-675 was inversely associated with fat-free mass, as was H19 in patients with COPD. So this associates with disease. So what can you do? So what's causing the association? Is it H19 or miR-675? Personally, I think it's both, because what H19 does is it binds these LET7 microRNAs. So to look at the involvement of the LET7 microRNAs, what we did was to develop some locked nucleic acid inhibitors of the interaction. When these bind to H19, they displace the microRNAs so that they can go on and function. If you look at their effect in cells, what you see is that H19 is suppressed, which is what you might expect, but so is MYC. And if you look at these two genes, these two locked nucleic acids, if you then look at the effect of TNF-alpha on IL-6 expression, you get a marked increase in the presence of both our control and our knockdown. But when you've blocked the association with the LET7s, you suppress that increase. If you put those into mice and do gene enrichment analysis, you find that you have got an elevation of the inflammatory response in the leg expressing the control compared to the two other microRNAs. Can we use any of this? Well, yes. If we look retrospectively at our cohort and measure the microRNAs and compare them to how much muscle they lose, if we take all the microRNAs we've measured, we can get quite good sensitivity and specificity for muscle loss. But this is only a single study. So just to finish, this is my model where we have inflammation or genes or disease-associated organ stress that elevates miR542 and 424.
I think your last slide hasn't changed. It was working perfectly up till then.
Oh. Hang on. Let me. What can you see now?
miR675 or its host gene H19.
Oh God, you're miles away. Something's gone wrong. Let me stop sharing.
I can see you're working around on your PowerPoint presentation. You're on miR675, and on the left is consequence, and you've got a flow chart.
Okay, that's fine. So you should be able to see environment. Can you see that?
Yes.
Yeah.
Yeah. Now we can see that.
Yeah.
Brilliant. Don't know what happened.
I think it was just a map problem. It's okay.
Okay. So we have disease-associated organ stress elevates these particular microRNAs. That causes mitochondrial ribosomal stress, mitochondrial dysfunction, cytoplasmic ribosomal stress, and a reduction in the ability to make proteins. If you are unfortunate, you are very susceptible to these changes and you get marked muscle loss. If you are at the other end of the spectrum and very resistant to those signals, you get minimal muscle loss. And of course, I didn't do any of that. These are the people who did. So if I stop sharing now.
Excellent. Thank you very much. We've got 2 minutes for questions. James, you've typed a question.